grade if you got a problem with attendance in a mini-term class, right? So what is a sensor? So the name of the class is AUT 232, Sensor Technology and Application. So the lab will be the application. And of course, we'll be talking about a lot of sensors that we're not going to do. But what is a sensor? Nobody here knows what a sensor is?
I don't know the definition.
So how would you define your senses? My brain has no idea what smell is. My brain has no idea what sight is. My brain has no idea what hearing is, right? My brain has no idea with touch what it is. So what does your brain basically process? Electrical signals, right? So I can come up here and I can touch something, and my brain says, okay, Rich, you've touched something. Even though my brain don't know touch, right? You understand? So what do these guys do out here? What are they doing? They're taking some type of physical stimulus and turning it into an electrical signal so my brain can process it. So what does these sensors do? Take a physical stimulus. Go ahead, Bernard. Takes a physical stimulus, right? And converts it over to electrical signals so we can process it with electrical equipment. So we can use them to bring in relays. We can input to a PLC. That's all PLC does. It works a lot like a brain, but it's not near as good at it. But all it does is look for electrical impulses to come in, and then it makes a decision on what to do with that, and eventually it outputs them. A device that converts a physical stimulus into electrical equivalent. And we'll look at something called a transfer function. The transfer function would be, our brain does it automatically, and sensors, we're going to have to figure this out. So, if I've got a weight sensor and I put a weight on a scale and it gives me an electrical voltage, I got to know what voltage equals what weight, right? Does that make sense? And we call a transfer function. So that'll be something we'll talk about. So it's the ratio between the physical stimulus and the electrical equivalent. That makes sense?
What, transducer, just another,
Transducer is a device. So a sensor, this is kind of, and you'll hear people call sensors transducers. A transducer is anything that takes energy in one form and converts it over to another form. So a sensor is a transducer, but a transducer does not have to be a sensor. It's just like me saying a Ford is a car, but a car don't have to be a what? Ford. So we could go down to Tannehill, and they got this big old grist mill out there. So what's it doing? It's a transducer, right? You understand? So what's it doing? It's taking the flow of water and converting it over to circular motion, right? You understand that? So we got all kind of transducers out there. So, and this should be in your glossary, guys, and I'm going to update that and put that up there. So we got a glossary of terms. And the way my glossary is set up, to make it easy for you, it's set up for classes. So there's a section in the glossary for sensors, and one of the definitions, of course, is sensor, and one of the definitions is transducer. And in the glossary, it'll say that it says a sensor will always be a transducer, right? You understand? But a transducer does not have to be a sensor. So, but what we do on these transfer functions is so if I had something that's got a linear output or a straight line output, we could literally say, okay, when I've got a sensor that outputs 10 volts when it sees 100 pounds, so I'd say 10 volts for 100 pounds, and what would that give me? 10 volts for 100 pounds, what would that give me? 10 divided by 100. So what we do on transfer function is this is the out, this is the in. So we're putting in weight and we're getting volts out, right? Understand? So I'd say transfer function would be the out over the in. So this would be in pounds. This would be in volts, right? You understand? And then we have what we call a transfer function. So what would that be? What's 10 divided by 100? It'd be 100 millivolts per pound. So here the pounds and the volts are not going to stretch out. So if I came over here and I had 200 millivolts, right? You understand? Makes sense? Okay, then I could come up here and do what? Multiply it by 200 millivolts, right? You understand that? Okay. Then what would my weight be? If it's 100 millivolts per pound, it's 100 millivolts per pound, then my weight would be 1 pound. Right? 200 millivolts for every pound. If I say it that way, does that make more sense? I'm sorry. 100 millivolts for every pound. So 200 millivolts means I would have what? 2 pounds. I said we're 2 pounds. Sorry. 300 millivolts would be what? 3 pounds. 400 millivolts would be 4 pounds. So now what I do is I could measure a voltage with my meter, and if I measured 200 millivolts, I knew it was what? 2 pounds. And that's what we did with the transfer function. So transfer functions are always what we get out. Of course, in our situation, just about every time it's going to be volts, because that's what we're trying to get to, right? And then we're going to put something into it like weight or speed or something like that. It'll be the input. We'll input on speed and we'll get so many volts out, which is what your car speedometer uses. Used to, car speedometers used a magnetic spinning wheel, and they'd put one inside the other, and they'd spin the outside. So you actually had a flexible metal rod coming up to your speedometer, and it's spinning around. And the speedometer had a spring on it, and depending on how fast the outside would spin, it would depend on how far the input went up there. But we don't do that now. How does a car speedometer work? Well, it works off of voltage, right? You understand that? If you got an analog speedometer, and that's still real popular on cars. They tried to put digital speedometers, purely digital speedometers in cars, and they were causing a lot of problems. You know why? Well, no, people wanted to look at them. So an analog speedometer, you've used your car so often, you don't even have to basically really look at it, right? You know if it about where it's at, you know about how far you're going. So that's why they all went back to analog, even though they look digital. So what are the 5 senses?
On the transfer function, like formula you just gave us, the out is going to be volts, is always be on top.
Well, I'm not going to say always, normally.
So like if you change it up in pounds to.
Yeah, we say, okay, speed. 10 volts for 100 miles, 10 volts for 100 miles an hour. Right? Understand? That makes sense now? So what are the 5 human senses, guys? Sight, taste, smell. Is that all?
No, you got more.
Oh yeah, we got that. So this is the one that we learned a long time ago. 5 things for years. And then people say, wait, there's more. What else can we sense? Balance. Yeah, we can sense balance, right? What else? They say today, the high today is going to be 50-some degrees, so we can sense temperature, right? That's not touch, that's temperature, right? You understand? What else can we sense? We can sense when we're hungry, right? That wouldn't be a sense, but, huh? So these are just a few. Temperature, we can sense temperature. We can sense the location of our parts. So I know where my arms are at. I know where my legs are at, right? You understand that? So that's pretty neat. We can sense pain. We can sense balance. We've already talked about that. We can sense pressure. We can sense hunger. We talked about that. thirst, which is a sense, right? Nausea. Anybody ever thrown up? Stretch receptacle, your lungs, your bladder, your stomach, your that stuff. So we know when we got to go to the bathroom, is what it's saying. We know when we got to breathe. So these are just some that just me researching the internet come up here. Just researching human system. This is what I came up. So we have two categories of sensors. We have analog sensors and we have digital. So analog sensors, whatever whatever quantity they provide is going to be constantly varied, right? But it's usually going to vary between 2 points, especially if you're using a voltage level. The minimum voltage you could get if we use like a 5-volt supply would be 0, right? You understand? And then the maximum would be what? 5 volts. But what's nice about analog is that it could literally go through an infinite number of combinations between 0 and 5. And I know it's hard for us to deal with infinity, but if you just think about the clocks, usually as far as we go down on our time is what? Seconds. Most of us don't even do that, but can we go further? Is there such thing as milliseconds and microseconds and picoseconds, right? And how far could we keep going? Yeah, basically forever. So advantage, it has an infinite number of values, which makes it more accurate. It requires less bandwidth than digital does. Low cost. The big disadvantage though is it's susceptible to electromagnetic interference. If I use voltage and then I have a magnetic wave pass through my conductor, it's going to try to induce a voltage into the conductor that might offset the voltage from my sensor, right? You understand? Hard to transmit over distance, so it's hard to maintain a voltage over distance. Because if we're going to use a voltage, odds are it's going to require a current, right? If it requires a current and there's resistance in the wire, then the wire is going to drop a voltage. Hard to store for later use. Hard to process by a computer, and it's hard for us to interpret. The analogy I like to use would be like I've got a flashlight. Even if the flashlight had 10 different locations and I had a switch, I could give you 10 different intensities. And then you try to interpret what numbers I would be sending you to that flashlight, it would be almost impossible for you to do that, right? That makes sense. And then if you went even further, it would do that. And if my batteries started going dead, then now what used to represent a 9 would now be, what used to represent an 8 would now be a 9. So analog is real hard to transmit. It's real hard to store for later use, right? And it's hard to process too, which is not that easy. It's hard to process. It's hard for a computer to process that. Digital, physical quantities vary in discrete steps. We can use either voltage or current. Of course, the most popular is voltage. Easier to process with the digital computer, easier to transmit, easier to store. A disadvantage, the resolution depends on the number of bits or binary bits. It makes it less accurate. And it costs a lot more money to send to use digital analog. So an analog system, control system, would be cheaper than if we start bringing in digital devices. If y'all had binary, anybody had binary numbers? PLC, y'all had PLC. And then the digital, you had that. So you can see, so if I've got 0 to 5 volts, if I'm doing that with analog, we could represent an infinite number of combinations. Digital, we might use 0 volts for a 0, 5 volts for a 1. So what we have to do is we have to start adding more what we call bits. We have to add more bits. So if I had 8 bits, I could only transmit 256 different levels. That makes sense? If I had 10 bits, that would still only be 1,024 different levels. But in analog, I could do 1,000 just with 0 to 5. I mean, I could do an infinite one with just what? 0 to 5 volts. So we start adding all these bits so we can get better resolution. cost a lot. A lot of your A to D converters, by the way, I know the one on the MicroLogic 1100 is a 10-bit A to D converter. Now, what an A to D converter does is that we can take the information coming from an analog sensor, and what we do is we bring it into an A to D converter, and then what it'll do is it'll give us a binary number that's equivalent, that's a representation of it. It'll never be an equivalent, right? Does that make sense? And so if we had a 10-bit A to D converter, that means we could only split the input into 1,024 different numbers, and there's nothing in between. So there's no such thing as a fraction. Does that make sense? Yeah. So if I was bringing 10 volts in, and then I would say, okay, I'm getting binary out, right, or 1,024 combinations, and then that would be what we call our volts per step. And there would be no fractions. It would either be, on this step, right, or it'd be what? It'd be on the next step. And you can see the more bits I add, the more accurate it gets, because my step sizes would become smaller, but then you're starting to add a lot of memory and stuff to your computer to be able to handle it. I think the 1200 has a 12-bit A to D converter, which would give us 4,096 different steps. So it's more accurate, right? You understand, but it takes more computer processing to handle that. So analog digital converters is just what we got into. We got different. So we got an analog to digital converter, and eventually, if we're going to control a digital device, if we're going to control an analog device with a computer, then computers don't understand analog, right? You understand? What do they understand? So we got two circuits that we have available to us. We have what we call a DAC, which is a what? Then we have an ADC, which is an analog to digital. Now, this is what we're doing though. On our A to D, we're going to represent a binary number, but we're going to take that input and actually come up with a number. We'll just throw something in here. So for this spot right here, it might come up and be, we'll just use a very simple one. It might be that number right there. And then up here, it might be what? It might be this number right here, right? You understand? And then that would be the peak, which might be that number right there. And then it would start dropping down. Okay. So what your PLC does, or your computer, it gets a binary number. But how accurate it is would depend on how many digits you have in your binary number. What we do when we go to an an analog to digital, is basically we take a waveform, we take a binary number, and we convert it into a step size. So what you end up with, your actual analog output is going to be in a sequence of steps. So it's still not pure analog, right? You understand? It's going to be steps, right? Does that make sense? And I wish I had my digital scope over here. So we got a digital scope, guys, and we could actually see the steps on the digital scope, because it's taking an analog input and converting it over to a digital representation. We can filter it out a little bit and make it look kind of neat. So for a DAC, and this is the problem we have with digital. So when I generate an analog waveform, it's going to be a sequence of steps. It's not going to be a nice, smooth waveform like a true analog would be, right? Does that make sense? Are you okay? So each binary number would represent a step. Okay. Huh? Okay. So sensor outputs, what's the most often used? Current, which was used a lot originally in controls. The advantage we have with current is electromagnetic interference, EMI, has a hard time creating a current. It can create a voltage, but it can't create a current. That makes sense? So what we'd have a low, but these guys, if it's a current interface, that means we're going to have a low resistance low resistance system, right? You understand? And these guys are going to conduct a current all the time. The most popular current out there is what we call a 4 to 20 milliamp current lead. So that means it's conducting a current all the time. When it's trying to send a 0, it's still going to send what? 4 milliamps if it was sending digital. When it would send to 1, it would be 20 milliamps. So this guy's constantly converting its current all the time. And it's going to be a low resistance system because we don't want a lot of resistance when we have current input, right? You understand? Because what would happen if we had a lot of resistance, then we'd drop a voltage, right? When we send voltage is used for using high resistance systems, which makes them susceptible to electromagnetic interference. But voltage is by far the most widely used, and we'll talk about some of the techniques that they're using now. Now, we can't use resistance, so if we've got a sensor that varies its resistance with what it measures, then somehow we're going to have to take that resistance and convert it into a voltage. That makes sense? Not hard to do. So if I had a temperature that changed its resistance, if I came up and did it like that, and this is the actual sensor, and we have a lot of sensors that vary their resistance. Now, what would vary with the sensor? I gave you that. So we got two things. We got current and we got voltage. And then we run the voltage, the current through a resistance, and it works, right? But what would change with this one? Either current or voltage? Which one? Current, yeah. So this guy right here would change current, right? You understand? Because the voltage itself would be constant. But if I was to come over here and do this, so that means if I was going to use this sensor, I would have to sense that current, right? You understand? But if I was to come over here and do the same thing and put a fixed resistor in here, and then put my sensor that varies with temperature, and then I take my output right here, I put my meter right there, then what would happen? Well, if the resistance went down, the voltage would go down, right? So total resistance would go down, total current would go up. This guy would drop more voltage, this guy would drop less. So this guy's going to make, this fixed resistor is going to make up the difference, right? Does that make sense? So if I start off and this is 0, if I have this set to 0 and I use 5 volts, that guy's going to set to 5 volts. If this guy drops 1, this guy's going to drop 4, right? You understand? If this guy drops 2, this guy here is going to drop 3, right? You understand that? But if I'm taking it across this guy right here, then the voltage is going to vary with whatever it measures. Does that make sense? Because Kirchhoff's law says the voltage has a drop. So, you know, like I said, if that was 5 volts, that means 5 volts had to be dropped across these two, right? You understand? Well, if this resistance goes down, it's going to drop less voltage. So if we start off with 0, this guy right here would be dropping what? 5. When this went up to 1, this guy here would have to do what? It would have to go to 4. And the current in the circuit's going to change because the resistance in the current's going to change to make this happen. Well, my meter would come over here and measure 1 volt. So here, and of course we could put it at the top. So we have to convert the voltage. We have to convert a resistance either into a current. So this would be a system that would convert it into current, but my whatever I'm sending it to would have to be here, right? You understand? Does that make sense? If I come over here and convert it into a voltage, then wherever I'm sending to can be over here. This is one reason why voltage is probably more popular. Sensor output. We can have, the output could have an AC output, which could be a thing called a triac. A triac is not really, so y'all had relays, right? You understand relays. So how does a relay work? Y'all gonna hurt my feelings if y'all don't know this. How does a relay work? Yeah, how does it work? How does it perform its function? I know what its function is, but how does it perform its function? First of all, we have a what? Of electromagnet, and that's what we call a coil, right? So it generates a magnetic field when we put a voltage across the coil. And what do we do with that electromagnet? We use it to open or close contacts, right? That makes sense. So that's all it is. That's all a relay is an electromagnet. And we looked at electromagnets next. And what advantage does an electromagnet have over a permanent? We can turn it on. That's what a relay does. We can either turn the magnet on or we can turn the magnet off. We turn it on, it's going to attract something, right? You understand? So it's going to attract that armature or that plunger that we said. It's going to cause that plunger to move, right? You understand? And it's going to change it's going to change the switches. So a relay is a electromagnetically controlled switch. But it's a electromechanical device, which means what? It can fail two ways. Well, a track, a lot of people call a track a solid state relay. Solid state means it has no movement. But what we do with a track, well, I can show you all the symbols, but we could draw it as a block too, but this is the symbol for a track. We bring our AC in here. So this would be AC, this might be AC in, and this right here might be AC out. And then we put a signal into it right here. And guys, when we call it firing, when we put a signal right here, so this would be called the gate. That sucker turns on and lets AC go through. We don't put a gate pulse on there, it turns off and AC. So it simulates a relay contact, right? You understand? But we don't have a watt. We don't have a coil. It's solid state. So we use these all over the place. I got lights at my house, motion detectors. When I walk outside, they come on. Well, there's no relays in that. It's got a track. It's a solid state relay. It's a solid state relay. You can buy solid state relays. That's what they're called. And they'll have two coil inputs, but they're not really inputs. They're just nothing but firing this track. So what's the advantage of a track is it has what? No moving parts. So you'll see a lot of these devices out there in sensors. So if I've got an AC sensor, like the ones we're going to have, odds are there is no relay in it. If it had a relay, what could you do? You could hear it click, right? So if you got a sensor that makes no noise at all when the simulated contacts actually go through, then it means that sucker's using a track for a. If it's an AC, if it's a DC, it's going to be something called a transistor, either NPN or PNP, and we'll have to learn about those too. That's for DC. Triacs would be for AC, and then transistors would be for DC. And then we have what we call single-ended differential. What they had, the problem we had with single-ended is that what they would do is they would come up here, and this is still extremely popular, guys, because it's so cheap. So to send information over wires, how many wires do we have? How many wires do we need? Anything over wires, how many do we need? Two, yeah. So we got to have at least two, right? That makes sense? Well, what they did for years, and they still do this, guys, and because it's so cheap, is that we would take one and we would reference it to circuit common. And we'd call that the common. And then the other one, we would call it the signal wire. Because that's the one we would actually measure it at, right? Understand? Now, what's the problem with this? Well, the problem with this, if we're in a real noisy environment, and I think I showed y'all the magnet over there, right? Didn't I show y'all that? Motor control. So anytime a magnetic field moves through a conductor, it wants an induced voltage into it, right? So what was happening was we'd come over here in industry, we got all type of magnetic interference. It's all over the place. So what happens if this EMI comes through these conductors right here? What would it try to do? It would try to induce a voltage into it. if it's using voltage as the method. And this is why the current loop in industry was so popular for so many years, because that voltage cannot, it's a voltage, but the only thing it would interfere with if our channels were extremely high resistance. So if this input over here was like 10 megohms, and then I put that pulse in there, there'd be almost no resistance out there to load that EMI, and it would cause the voltage to change. But if I came over here and used current in a current loop and don't use a ground reference, and then we're going to be dealing with this guy here might be 10 ohms. Now when the EMI come into this, it can't, the voltage it tries to put into it would not be, it's like static electricity. So static electricity, how much work can you get out of static electricity? You can fire off a fluorescent bulb, but that's about it. The resistance of a fluorescent bulb is extremely high. But what happens as soon as you try to get work out of it, the resistance of your body loads your current down, the voltage drops off instantly, right? You understand? So that's why you can't kill somebody with static electricity. You can scare them, but you can't kill them. Because as soon as you touch something and that arc appears, then the voltage drops down to what? Drops down to 0 instantly. You're at the same potential almost instantly. So you're a high resistance source, right? You understand? But you pick up voltage all the time. But that voltage that I pick up, I can't get any work out of it. So what we're saying over here, if this is 10 megohm, which is about what your resistance is, then if I tried to get work out of this, I couldn't get, I can induce a voltage into this, right? You understand that? But over here, if I try to get work out of it, the voltage will drop down instantly. So this is why the 4 to 20 milliamp was so popular, because it was almost immune to electromagnetic interference. And you're still going to run into it in older plants. There's no doubt about it. In fact, you can still buy interfaces for programmable logic controllers that run 4 to 20 milliamp signal. So single-ended, this was single-ended. Single-ended is when you reference one of your conductors to what? To common, and then you have the other conductor that has a signal wire. This single-ended was pretty susceptible to electromagnetic interference. So what they did, and this is what just about all our communication standards use right now, USB, Ethernet, just about all our the telephone system is actually the first one that came up with this interface, by the way, to reduce noise. Is they decided not to use common. So what do we need to make current flow? We always got to have a difference in potential. Does that make sense? So if I send in digital information over here, and this could be analog too, but digital is easier to see. What they would do is they would use one conductor, and they call it the plus, not because it is a positive signal, is because it's what we call the non-inverting signal. And then what they would do on your other wire is they'd send the mirror image of this. And if you ever look at an RS-232 interface, it's going to have a plus and a minus. And then it's going to have DC on it. Not RS-232. Now what they devised was a special amplifier that they call a differential amplifier. And what it would only do, what it would only let come through would be the actual difference. So as long as I have a difference, then it would come through. And what you would, go ahead.
So the exercise you got right there, it's a mirror image.
Well, that's what we get, and that's why we get a current flow. Even though there's almost none in it, this is still a high resistance system. But I always have so I always have a difference. So notice here, this would be a plus, and this right here would be a minus. So we have a difference in potential. Yeah. Okay. Does that make sense? So, but we don't use 0 volts as a reference anymore, right? You understand that? Exactly what you said. We would have a positive voltage and we would have a negative voltage all the time. But every time we're sending something, we'd always have a difference in potential. And what the differential amplifier would do, what it does is only let what's moving in different directions pass through. So what that means is if I had electromagnetic interference come through in here, it would induce a voltage into this guy, and it would induce a voltage into that guy, right? But these guys are moving in the same direction. This is what became known as common mode signals. So what would happen is that this guy over here would only, if it only lets differential signals come through. So these guys right here would be common mode, and what would it do? It would block those. And this came up a common. You can actually see this. They call it a common mode rejection ratio. So one of the things I give you, and it's up in thousands. So that means common mode signals. If I've got a common mode signal of 2,000, that means 1/2000th of a common mode signal would have the ability to get over to the output. Now this has revolutionized sending information. So we don't see, in sending information, we don't see using common mode signals very often because we have problems with what? We have to shield them. So just about all your signals that use common modes have a shield on it. We'll look at that. That's a metal antenna that's out there that's preventing the EMI from getting into the actual conductor. So just about all our channels and a lot of our sensors out there. So we have sensors that we can hook up directly, but it's becoming more and more popular in automated systems. So I could have a sensor here, a sensor here, a sensor here, a sensor here, and a sensor here. And then I'd have to run 2 wires from this guy, 2 wires from that 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 guy. Or I could come over here and have a bunch of sensors and hook it up to a common wire. So what I'm doing is I'm only running one wire back to my computer. And this is these sensors, most of our sensors now are becoming probably what we call networkable, which means we can hook them up to one of our industry standard networks, like Profibus, Fieldbus, Ethernet IP, which is almost identical to Ethernet, because all those use differential signaling, which means now instead of running 2 wires all the way back, we can run 1 wire. And when we're over there when we're over there in the lab over there, we'll show y'all the Profibus in fact, some of y'all probably seen it, where we've got all the PLCs connected together. And over there on the robot, we'll probably run that thing down and let you see that it's all hooked. We got all these guys up on top of that robot, but they all come out of one cable. So we're not running individual wires anymore. We're networking. These guys are networkable now. All our sensors do. So we can buy different interfaces to like for PLCs where we can handle these networkable sensors. And just about all these use differential signals. So this differential signaling basically eliminates the electromagnetic interference. So like an Ethernet cable, we can run an Ethernet cable. I don't know if we got one in here or not. It's good for 100 meters before you have to re-amplify and send it on. So we can run an Ethernet cable because it uses, and that's through some pretty noisy environments. We can run that'd be over 330 feet that we can run an Ethernet cable. In the old serial interfaces, we were dealing with feet. Single-ended used to be, unshielded single-ended would be maximum would be 15 feet. Y'all know what we mean by shielded, right? Yes or no? So what we do is we'll take our two conductors and then we'll wrap them in metal braid. And that metal braid is called a shield. And it'll be metal. And then what we'll do is we'll take one end and we'll connect one end to the common. And so when we generate electricity, it's referenced to common. So what would happen is your electromagnetic interference would come in here and hit your shield, and it would be shorted to ground. But a shielded cable costs a lot more than an unshielded cable. So that's why Ethernet, we can buy shielded Ethernet cables, and I'll show you that too when we go over there. So these are just some basic terms we'll be looking at. All ours are going to be, all our sensors are going to be similar. But they'll probably be shielded, right? Understand that? Makes sense, huh? So a shield, by the way, guys, no matter what you tell, a shield should only be grounded on one side. If you ground it on both sides, it becomes a conductor. We want it to be an antenna. We want it to grab the EMI and send it to ground, right? We don't want it to be a conductor. So shield should only be grounded on one side. So we'll look at some Ethernet switches that we got in the metal over there that's designed to do this. So this will be on the lecture. So what we're gonna do right now is we're gonna take a break and we're gonna meet back over at the mechatronics lab. You know where that's at? And we'll look at a bunch of sensors over there. We'll look at some of the technology that's available, and then